When two or more things happen at the same time, we say that they happen simultaneously. When we have two or more equations and we need solutions which satisfy all of the equations, we say that we have simultaneous equations. There are several ways to solve these. Let's start by looking at this as an example. So we have an equation 2x subtract y is 1, let's call that equation 1, and x plus y is 5, let's call that equation 2. The first way we're going to look at to solve this is called substitution. When we use substitution, we take one of the equations, let's say equation 1 in this case, and rearrange it so that it is of the form x equals or y equals. It's very easy to see that equation 1 can be written as y is equal to 2x subtract 1. Having done this, we now substitute this expression for y into the other equation. So we have x plus, and instead of y, we'll now write 2x subtract 1 is 5, and we have to carry on and solve that equation. We have x plus 2x, so we have 3x's, subtract 1 is 5, so 3x is 6, and so x is 2. Now we don't just need the value of x, we'll need the value of y as well. So using our rearranged version of equation 1, y is 2 lots of x, which we now know to be 2, subtract 1, in other words, y is 3. And it's a good idea to write a conclusion at the very end so that nobody has to dig through all of our working to find the values of the variables under question. So here we are, x is 2, y is 3. Another approach is to use elimination. In elimination, we find a way of combining the equations which eliminates one of the variables. For example, if we take equation 1 and add equation 2, then on the left-hand side we'll have 2x's plus another x, we'll have 3x's. We'll have a negative y and a positive y, but they will cancel out. On the right-hand side we have a 1 and a 5, which is 6, and so dividing by 3, we have that x is 2. We still need the value of y, so we can use either of the equations. Let's use equation 2 to say that x, which we now know is 2, plus y is 5, and therefore y is 3. Once again, let's finish with the conclusion: x is 2, y is 3. There we are. There is a nice way of visualizing this sort of situation as well. If we were to draw the straight lines that correspond to those two equations, one for 2x subtract y is 1, one for x plus y is 5, then everywhere on the green line it is always true that for any point on there with xy coordinates, 2x subtract y is 1, and for any point on the blue line with xy coordinates, x plus y is 5. So the place where both of those equations are true at the same time is the one place where they intersect. And that intersection value has coordinates 2, 3. Therefore the solutions to these simultaneous equations are x is 2 and y is 3. If you have a really nice picture already drawn, or if you have some graph paper available, this is a third method which will work perfectly well. However, it's better for us to be thinking algebraically wherever we can. In this example, we have the simultaneous equations 3x subtract y is negative 7, let's call that equation 1, and 2x plus 3y is 10, let's call that equation 2. So let's solve them first of all by substitution. Equation 1 can be rearranged so that it is y is 3x plus 7. If we then substitute that into equation 2, we get that 2x plus 3 lots of 3x plus 7 is equal to 10. So now we just have to work on this until we have a value for x. 2x plus 9x plus 21 is 10. So altogether we have 11 x's, and if we subtract the 21 from both sides, that's equal to negative 11. So now we can see that x is negative 1. And using our rearranged version of equation 1, we have that y is 3 lots of negative 1 plus 7. In other words, y is 4. In conclusion, x is negative 1, y is 4. Alternatively, we could do this by elimination, but this time just adding the two equations together is not going to eliminate anything. We would have to do something like this. Maybe we should take 3 lots of equation 1 and then add equation 2. Because 3 lots of equation 1 would give us 9 x's from the first equation and 2 x's from the second one, therefore we'd have 11 x's. It would give us negative 3y from the first equation and 3y from the second equation, so no y's at all. And negative 21, because that's 3 lots of negative 7 from the first equation, and 10 from the second equation, which added together give us negative 11. And then we can see, as before, that x is negative 1. Now how could we get the value of y? Let's use equation 1. 3 lots of x, which is negative 1, subtract y is negative 7. In other words, negative 3 subtract y is negative 7. And so y is 4. We have an x of negative 1 and a y of 4. And again, we can see this graphically. If we draw straight lines corresponding to those two equations, then their intersection point will be the point which is a solution to the simultaneous equations, which in this case is the point negative 1, 4, x is negative 1, y is 4. Now all of the examples we have been considering so far have consisted of two linear simultaneous equations, ones where the highest power of x and y is 1. And here is one more example of that. So let's call this equation 1 and this equation 2. If we are to do this by substitution, we have to take one of those equations and rearrange it to make it x or y equals. Let's take equation 2 because that's going to be substantially simpler. And why don't we rearrange for x this time? We'll have that 2x is negative 6y, subtract 1, and therefore x itself is negative 3y, subtract 1/2. Now if we take this and substitute it into equation 1, we'll get that 30 lots of negative 3y, subtract 1/2, subtract 12y is 19. That means we'll have negative 90y, subtract 15, subtract 12y is 19. How many y's do we have altogether? Negative 102 y's. If I add the 15 to both sides, that will be equal to 34, giving us a y of negative 1/3. We now need an x value, but we already have an expression for x in terms of y, because x is negative 3 lots of y, which is negative 1/3, subtract 1/2, which is 1, subtract 1/2, which is 1/2. So our conclusion is that x is 1/2 and y is negative 1/3. Using the alternative of elimination, we could do equation 1 and 2 lots of equation 2. How many x's would we have? 30 from equation 1 and 4 from equation 2, because we've got 2 lots of that equation. So we would have 34 x's. But then negative 12y from equation 1 and 2 lots of 6y, which is 12y from equation 2, they will all cancel out. On the right hand side, we'll have 19 from equation 1 and negative 2 from equation 2, so we'll have 17. So we straight away get that x is 17 divided by 34, 1/2. Now we could use equation 2, say, to say that 2 lots of x, in other words 2 lots of 1/2, plus 6y is negative 1. 1 plus 6y is negative 1. So 6y is negative 2, and dividing through by 6, y is negative 1/3. So we have the same conclusion, that x is 1/2 and y is negative 1/3. It does not matter which method you use to solve these simultaneous equations, but it is a very good idea to be capable of doing it either way. Once again, we could visualize this by plotting graphs of the two straight lines and their intersection point. 1/2, negative 1/3, is the solution we want. If you do not have integer solutions, then a graphical method can be a little difficult to interpret. In this example, although the first equation, equation 1, is a linear equation, equation 2 has a power of x of 2 in it. This is a quadratic equation. So it is not always the case that both of our equations will be linear. Here we have one linear and one quadratic equation to solve simultaneously. When we have this situation, it is almost always easier to do it using substitution. So if we take equation 1, we can rewrite that as y is 2x subtract 7. We can then substitute this into equation 2, where we have x squared subtract 6x subtract 2x subtract 7 is negative 5. Now we have an equation which is just in x, so let's tidy it up and see if we can solve it. X squared subtract 6x subtract 2x plus 7, and let's also add the 5 to both sides as well, is equal to 0. So we have the quadratic x squared subtract 8x plus 12 is 0. Let's optimistically hope that we can factorize that. It doesn't take an awful lot of thought to realize that yes, we can. We have x minus 6, x minus 2. So either x is 6 or x is 2. And already we have a big difference to the examples we've already looked at, in that there is more than one possible value of x. In each case we'll need a corresponding value of y, and we know from the very first thing we did here that we can get our values of y by doing 2 times our values of x, subtract 7. So y is either 2 6's subtract 7, or it's 2 lots of 2 subtract 7. In other words, y is 5, or y is negative 3. It is very important to pair up the right values of x and y, so as a conclusion I would say that either x is 6 and y is 5, or x is 2 and y is negative 3. We can interpret the fact that we have two solutions graphically. We are looking at the intersection of a straight line and a quadratic. And we can see that these do intersect at 2 points, once at the point 2, negative 3, and once at the point 6, 5, which correspond to our two sets of solutions. This diagram shows that we may have several different situations when we have a straight line and a parabola. We may be in the situation we have just shown, where they intersect in 2 different points, or we may be in a situation where they do not intersect at all, or we may be in a situation where the line just touches the parabola, so there is one solution. There is an algebraic way that we can determine which of these situations we are in. We will illustrate this with the following example. The line y equals 4x plus 3 and the curve y equals x squared plus kx plus k plus 2 meet at exactly 1 point. Find the possible values of k and the coordinates at the point of intersection for each of these values of k. So if we have that y is 4x plus 3 and y is also x squared plus kx plus k plus 2, then those two expressions will be equal to each other. We'll have that x squared plus kx plus k plus 2 is the same thing as 4x plus 3. Let's rearrange that so we have everything on one side. X squared plus kx, subtracting a 4x from the other side, plus k plus 2, subtracting the 3 from the other side, that's all equal to 0. So tidying this up as a nice quadratic, we'll have x squared. How many x's will we have? K subtract 4 x's, and what number will we have on the end? K subtract 1. That's equal to 0. Now if we are told that the line and the curve meet at one point, that means there will only be one solution to this equation. And if we only have one solution to a quadratic equation, we have a way to identify that. That means that the discriminant of the quadratic equation is 0. What is the discriminant of this quadratic equation? B squared. B is how many x's we have? We have k subtract 4 x's. So b squared subtract 4 times a, which is 1, times c, which is the number on the end. Our number here is k minus 1. All of that will be 0. So let's expand. K squared subtract 8k plus 16. And from the second term, subtract 4k plus 4. All of that is 0. Simplifying, we have that k squared subtract 12k plus 20 is 0. And again, optimistically hoping we can factorize this. And yes, we can. That will be subtract 2, subtract 10. So the possible values of k are that k is 2 or that k is 10. How can we find the point of intersection for these values? Let's do them one at a time. If k is 2, what do we have? Well, we already have this quadratic equation on this line, which we know must be satisfied by the value of x. So let's see what that equation becomes when k is 2. We have x squared subtract 2x plus 1 is 0. That simplifies to x subtract 1 squared is 0. Because we know there is only going to be one solution, we should always end up with an expression of the form x plus or minus a number squared is 0. So the value of x is 1, and the value of y that goes with that is 4x plus 3, y is 7. So in the case where k is 2, we have an intersection point of 1, 7. In the case where k is 10, we can again go back to the quadratic we know and say that we'll have x squared plus 6x plus 9 is 0, which once again we can immediately factorize into a form x plus a number squared is 0, in this case x plus 3 squared, so x is negative 3. And again, the value of y is 4 times the value of x plus 3. In this case, y is negative 9. So the point of intersection in this case is negative 3, negative 9. Let's look at that graphically. We have this straight line, and when k is 2, we have this parabola. They intersect at the point 1, 7. When k is 10, we have a very different parabola. which we are going to have to zoom out to see at all. But here we have an intersection point of -3, -9. We may have a quadratic equation which doesn't actually have a square in it. If we multiply an x and y together, that still counts as quadratic. So can we solve the simultaneous equations x plus y is 5 and xy is 5? Well, equation 1 is easily rearranged to give us that y is 5 subtract x. If we substitute that into equation 2, we get that x times 5 subtract x is 5. Let's try and work on this. That gives us that 5x subtract x squared is 5. Rearranging that into a quadratic, putting it all on one side, we have x squared subtract 5x plus 5 is 0. Oh, can't see any obvious way to factorize that. In fact, let's just check. Discriminant in this case is -5 squared subtract 4 times 1 times 5. It is 25 subtract 20, which is 5. So no, 5 isn't a square number. We're not going to be able to factorize that. Let's solve it by completing the square. So I will have x subtract 5 over 2 squared subtract the -5 over 2 squared plus 5 is 0. In other words, x subtract 5 over 2 squared subtract 25 over 4 plus 5 is 0. X subtract 5 over 2 squared is 5 over 4. So taking the square root of both sides, x subtract 5 over 2 is plus or minus root 5 over 2. So x is 5 over 2 plus or minus the square root of 5 over 2. We could write our two answers as either x is 5 plus the square root of 5 over 2, or x is 5 subtract the square root of 5 over 2. We're going to need the y values that go with that. In this case, we will have 5 subtract 5 plus root 5 over 2. In this case, we'll have 5 subtract 5 plus root 5 over 2. The first of these gives us 5 plus root 5 over 2, while the second gives us 5 subtract root 5 over 2. I know there feels like there's an awful lot of symmetry and things going on here, but when you look back at the original equations we're trying to solve, that's not surprising. So our conclusion would be that either x is 5 plus root 5 over 2 and y is 5 subtract root 5 over 2, or vice versa. The x could be 5 subtract root 5 over 2, the y could be 5 plus root 5 over 2. A comprehensive final example to finish us off. Let's solve this one linear, one quadratic simultaneous equations, again by using substitution. So equation 1 can be easily rearranged into y is 3 subtract 2x. If we substitute that into equation 2, we'll have that 3 subtract 2x squared plus x into 3 subtract 2x plus 16x is 13. This equation just has x in, but we've got a bit of algebra to do to solve it. So expanding the first square bracket, we'll have 9 subtract 12x plus 4 x squared. Expanding the next bracket, we will have 3x, subtract 2x squared. We've also got that 16x, and let me subtract the 13 from both sides so that everything is together. How many x squared do we have altogether? 4 subtract 2, we've got 2x squareds. How many x's? 16, take away 12 is 4, plus 3 is 7. Numbers, 9, take away 13, negative 4. Let us optimistically assume this is going to factorize, in which case it must be a 2x and a single x. We will need two numbers which multiply to negative 4. Yes, that is going to be plus 4 minus 1. So we have an x of a half or an x of negative 4. And the y values that go with them will be a y of 3 subtract 2 lots of a half, or 3 subtract 2 lots of negative 4. So we will have a y value of 2 or a y value of 11. So our answers are either x is a half and y is 2, or x is negative 4 and y is 11.